Hello and welcome to Space Historians. I am glad you have joined me here, in this quiet moment where the day can finally settle and the mind can drift towards something larger than itself. Tonight, we will explore one of the most profound questions humans have ever asked. How big is the universe compared to our galaxy? It is a question about scale, about perspective, about standing beneath the night sky and wondering just how far the darkness extends. Each episode here is a gentle invitation to step away from urgency and into curiosity, to let science become a companion for rest rather than a demand for attention. If you find these journeys soothing, a like or subscribe helps others discover this quiet space. But for now, you need do nothing except listen, breathe, and let your thoughts wander outward, where the stars wait patiently to tell their story. There is a moment that comes to almost everyone at some point in their lives, often unexpectedly, when the night sky stops being to merely background and becomes something else entirely. Perhaps you're standing outside after a long day, the air cool against your skin, and you glance upward out of habit. Or perhaps you are far from city lights, camping in the wilderness, and the darkness is so complete that the stars seem to multiply before your eyes, revealing layers upon layers you never noticed before. In that moment, something shifts. The stars are no longer just points of light. They become distances, histories, worlds. And with that shift comes a question, sometimes spoken aloud, sometimes whispered only in the mind. How far does all of this extend? Tonight, we are going to explore that question together, slowly and gently, letting each piece of understanding settle before moving to the next. We are going to compare two scales that seem almost impossible to hold in the same thought. The Milky Way, our home galaxy, vast beyond everyday comprehension, and the universe itself, so much larger that the comparison challenges the very limits of imagination. This is not a race toward numbers. It is a walk through perspective, a journey that asks you to stand still beneath infinity and simply notice what it feels like to be small, connected, and aware. Before we begin properly, let me ask you something simple. Where are you right now? Are you lying in bed, perhaps with the curtains drawn and only the faint glow of a screen or lamp to keep you company? Are you sitting in a chair, wrapped in a blanket, the sounds of the house settling around you? Or are you somewhere else entirely, on the other side of the world, where daylight still lingers but you have come here seeking calm? Wherever you are part of this journey. You are standing, in a sense, beneath the same sky I am describing, even if you cannot see it at this moment. The stars are there, beyond the ceiling, beyond the clouds, beyond the daylight. They are always there, waiting. If this kind of exploration brings you peace, if the slow unfolding of cosmic scale helps your mind release the tensions of the day, I would be grateful if you tapped the like button or subscribed. These small gestures help others find this space, this quiet corner where science meets sleep, where curiosity becomes a lullaby. But there is no pressure. For now, simply let yourself settle. Let your breathing slow. Let the day fall away. We are going to step outside together, in our imagination, and look up. Picture yourself standing in an open field at night. The ground beneath you is solid, familiar. The air is still, cool enough to notice but not uncomfortable. Above you, the sky stretches in every direction, a dome of darkness punctuated by light. If you are lucky, if the conditions are right, you can see the Milky Way itself, a pale, glowing band that stretches across the heavens like a river of faint light. This band is our galaxy seen from the inside, the combined glow of billions of stars too distant to distinguish individually, but close enough that their light reaches us, blending into that soft, hazy ribbon. Most people see the Milky Way only a few times in their lives. City lights wash it out, turning the night sky into a handful of bright stars against a brownish glow. But when you do see it, truly see it, the effect is profound. You realize that you are not looking at something separate from yourself. You are looking through the structure you already inhabit, seeing your home from the inside. Every star in that band, every faint smudge of light, is part of the same galaxy that contains our Sun, our Earth, and everything we have ever known. The Milky Way is not just above you. It is around you, through you, in you. You are inside it, and that realization can be both grounding and disorienting. But the Milky Way, vast as it is only the beginning of the story. Because if you could zoom outward, if you could rise above the galaxy and see it from the outside, you would see something even more astonishing. The Milky Way is just one island in an ocean of darkness. Around it, separated by immense gulfs of empty space, are other galaxies. Some are nearby, like Andromeda, visible as a faint smudge to the naked eye on a clear night. Others are so distant that their light takes billions of years to reach us. And beyond those, farther still, are trillions more, scattered across a volume of space so large that even light, the fastest thing we know, takes tens of billions of years to cross it. This is the hook, the moment when the question crystallizes. How big is the universe compared to our galaxy? It is a question that sounds simple, but opens into something vast and layered. To answer it, we will need to understand what a galaxy is, how we measure distances so large that normal units become meaningless, and what it means to live inside a structure that is itself just a speck in something unimaginably larger. But before we dive into those details, let us simply sit with the feeling of the question itself. Let it settle. Let it become less about numbers and more about perspective. The Milky Way is about 100,000 light years across. That means light, travelling at 300,000 kilometers per second, takes 100,000 years to cross from one side to the other. To a human, that is incomprehensible. We do not live long enough to even begin to grasp such a timescale. And yet, compared to the universe, the Milky Way is tiny. The observable universe, the part we can see, stretches about 93 billion light years across. That is nearly 1 million times wider than our galaxy. If the Milky Way were the size of a coin, the observable universe would be larger than the Earth itself. And beyond what we can see, the universe may continue indefinitely, perhaps infinitely, into regions we will never observe. To stand beneath the night sky with this knowledge is to feel something that words struggle to capture. It is not quite fear, though there is an edge of vertigo to it. It is not quite loneliness, though there is a recognition of smallness. Perhaps it is closer to awe, that particular mixture of wonder and humility that comes when the mind brushes against something too large to hold. You are small. Yes. Your life is brief. Your concerns are local. But you are also part of this. The atoms in your body were forged in stars that lived and died billions of years ago. The light you see from distant galaxies left those galaxies when the Earth was young, travelling across space to arrive at your eyes in this moment. You are not separate from the universe. You are one of the ways it looks at itself. This is the hook. Not a fact to memorize, not a number to calculate, but a feeling to carry with you as we move forward. The universe is vast. Our galaxy is vast, and the difference between them is so large that it challenges the imagination. But tonight, instead of being overwhelmed by that difference, we are going to walk through it slowly, step by step, until the scale becomes less alien, and more like a map we can hold gently in our minds. We are going to build an understanding not through memorization but through patient accumulation, letting each layer rest before adding the next. So take a breath. Notice the ground beneath you, real or imagined. Notice the sky above, whether you can see it or only picture it. We are standing beneath infinity, you and I, and we are about to take the first step outward. The journey begins here, in this moment, with the simple act of looking up and asking how far the stars extend. The answer, as we will discover together, is farther than we can fully grasp, but close enough that we can trace its outline, one gentle step at a time. To understand how the universe compares to our galaxy, we must first understand where we are. not just geographically, not just in terms of city or country, but cosmically. We need to establish our address in the largest sense possible, starting from the smallest scale and moving outward, step by step, until we can see the entire nested structure that defines our place in existence. This is not about memorizing a list. It is about feeling the layers, about understanding that each scale is both enormous and contained within something even larger. So let us begin where all addresses begin, at home. You are on Earth. That seems obvious, but it is worth saying aloud, because Earth is not just our home. It is also a planet, a world, a sphere of rock and water, and air spinning through space. Earth is about 12,700 kilometers across, small enough that airplanes can circle it in less than 2 days, but large enough that most of its surface remains unfamiliar to most of its inhabitants. To you, Earth feels vast. Oceans stretch beyond sight. Mountains rise higher than you can easily climb. Forests extend for hundreds of kilometers. The scale of the planet dwarfs the scale of human life, and for most of history, Earth was all there was. The sky was a dome, the ground was flat, and beyond the horizon lay only more of the same. But Earth is not alone. It orbits the Sun, a star, one of the most fundamental objects in the universe. The Sun is about 1.4 million kilometers across, more than 100 times wider than Earth. It contains 99.8% of all the mass in our solar system, and its gravity holds everything else in orbit. 8 planets, countless moons, asteroids, comets, and dust. The distance from Earth to the Sun is about 150 million kilometers, a gulf so large that light takes 8 minutes to cross it. This distance defines what astronomers call an astronomical unit, or AU, the basic measuring stick for the solar system. When we say Neptune is 30 AU from the Sun, we mean it is 30 times farther than Earth, nearly 4.5 billion kilometers away. The solar system itself is only a small part of the Milky Way galaxy. To picture this, imagine shrinking the Sun to the size of a grain of sand. On that scale, Earth would be a speck of dust orbiting a few centimeters away. Neptune would be about a meter away, and the nearest star, Proxima Centauri, would be more than 4 kilometers away. Space is not crowded. It is almost incomprehensibly empty, with islands of matter separated by vast oceans of nothing. The solar system, for all its planets and moons, occupies only a tiny bubble in the Milky Way, a bubble surrounded by light years of darkness before you reach the next star. The Milky Way is a spiral galaxy, a flattened disk of stars, gas, and dust with graceful arms curling outward from a central bulge. It contains between 200 and 400 billion stars, each one a sun in its own right, many of them with planets. The Milky Way is about 100,000 light-years across and roughly 1,000 light-years thick. Our solar system sits about 27,000 light-years from the center, on the inner edge of a spiral arm called the Orion Arm. This location is neither central nor peripheral, but somewhere in between, a middle-class neighborhood in a galaxy full of stars. From our vantage point inside the Milky Way, we see it as a band of light stretching across the night sky. When you look toward that band, you are looking through the plane of the disk, seeing the combined glow of billions of stars. When you look away from it, you are looking out of the disk, where stars are more sparse. The Milky Way is not something we can step outside and photograph from above. We are inside it, embedded in it, and every observation we make is shaped by that perspective. Mapping our own galaxy is like trying to map a city while standing in the middle of it, unable to see beyond the buildings immediately around you. But the Milky Way is not alone either. It belongs to a group of galaxies called the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group spans about 10 million light-years across, and the Milky Way shares it with another large spiral galaxy, Andromeda, along with dozens of smaller dwarf galaxies. Andromeda is about 2.5 million light-years away, close enough that it is visible to the naked eye as a faint smudge on clear nights. In about 4 billion years, the Milky Way and Andromeda will collide, merging over billions of years into a single larger galaxy. For now, they drift toward each other, two islands in the same small archipelago. The local group, in turn, is part of a larger structure called the Virgo supercluster, now known to be part of an even larger structure called Laniakea. Laniakea spans about 500 million light-years and contains roughly 100,000 galaxies, all flowing along gravitational currents toward a region called the Great Attractor. These flows are like rivers in the cosmic landscape, shaping how galaxies move and cluster. The Milky Way is not just sitting still in space. It is drifting, carried by currents of gravity that span hundreds of millions of light-years, and Laniakea itself is just one supercluster among many. The universe is filled with such structures, separated by vast voids where almost nothing exists. When astronomers map the large-scale structure of the cosmos, they see a web-like pattern. Filaments of galaxies stretching across hundreds of millions of light-years, walls where galaxies cluster densely, and voids where darkness dominates. This cosmic web is the largest structure we know, and it fills the observable universe, which stretches about 93 billion light-years across. So here is our cosmic address, written from smallest to largest. Earth, orbiting the Sun, in the solar system, located in the Milky Way galaxy, part of the local group within the Virgo supercluster, itself part of Laniakea, situated in the cosmic web within the observable universe. Each layer is contained within the next, and each layer represents a jump in scale, so large that it strains comprehension. From Earth to the solar system is a jump of billions of kilometers. From the solar system to the Milky Way is a jump of trillions of kilometers, or thousands of light years. From the Milky Way to the local group is a jump of millions of light years. From the local group to Laniakea is a jump of hundreds of millions. And from Laniakea to the observable universe is a jump of tens of billions. This nested structure is the setting for our exploration tonight. We live inside it, moving through it, and yet most of the time we are unaware of it. Our daily lives unfold on the scale of meters and kilometers, seconds and hours. We notice the weather, the landscape, the buildings around us. But we do not feel the motion of Earth through space, the orbit of the solar system around the galactic center, or the drift of the Milky Way toward Andromeda. These larger scales are invisible to direct experience. They reveal themselves only through measurement, through careful observation, through the slow accumulation of knowledge. To know our cosmic address is to know that we are deeply embedded in a hierarchy of scales. It is to know that home is not just a house, or a city, or even a planet, but a galaxy, a supercluster, a universe. It is to know that the boundaries we draw around ourselves, the edges of our property, the borders of our countries, are arbitrary compared to the natural boundaries of gravity and light. And it is to know that the question we are asking tonight, how big is the universe compared to our galaxy, is really a question about stepping outward through these layers, comparing the container to what it contains, the whole to one of its parts. The setting is vast, but it is also structured. The universe is not a random scattering of matter, but a hierarchy of nested systems, each held together by gravity, each moving in response to the masses around it. To understand this setting is to see that we are not adrift in chaos, but embedded in order, participants in a cosmic architecture that stretches from the surface of Earth to the farthest reaches of space. This is where we live, this is where we stand, and from here we can begin to compare the size of our galaxy to the size of the universe itself, knowing that both are part of the same continuous structure, both pieces of the same vast puzzle. For most of human history, the Milky Way was not understood as a galaxy at all. It was simply the sky, a feature of the heavens, a glowing band that stretched from horizon to horizon on clear nights. Ancient peoples wove stories around it, calling it a river, a path, a bridge between worlds. But no one knew what it truly was. No one imagined that the stars themselves were suns, that the faint glow was the combined light of billions of distant fires, or that beyond the Milky Way lay an entire universe of other galaxies. The discovery that our galaxy is just one among many, and that the universe extends far beyond it, was not a single moment of revelation, but a slow unfolding of understanding that took centuries and culminated in one of the most important debates in the history of astronomy. The story begins with the invention of the telescope in the early 1600s. When Galileo turned his simple instrument toward the Milky Way, he saw something astonishing. The hazy band resolved into countless individual stars, too faint and too numerous to see with the naked eye. This was the first hint that the Milky Way was not a cloud or a celestial river, but a vast collection of stars. But even then, the scale was unclear. Were these stars part of a finite system, or did they extend infinitely in all directions? Was the Milky Way the entire universe, or was it just a piece of something larger? For the next 2 centuries, astronomers debated the structure of the cosmos. Some believed the universe was infinite, filled with stars in every direction. Others believed the stars formed a flattened disk, a system with boundaries, beyond which lay only darkness. But the key question that would eventually reshape everything was about the spiral nebulae, faint fuzzy patches of light visible through telescopes. Were these nebulae clouds of gas inside the Milky Way, or were they separate systems, entire galaxies in their own right, lying far beyond the edges of our own? By the early 20th century, this question had become urgent. Telescopes had grown more powerful, and astronomers could see that some of these nebulae had spiral structures, elegant arms curling outward from a bright centre. They looked almost like smaller versions of the Milky Way, which led some astronomers to suspect they were island universes, distant galaxies comparable to our own. But others argued that they were simply nebulae within the Milky Way, glowing clouds where new stars were forming. The debate split the astronomical community, and for years, neither side could prove their case conclusively. The turning point came in 1920, in an event now known as the Great Debate. 2 prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views at the National Academy of Sciences in Washington, D.C. Shapley argued that the spiral nebulae were part of the Milky Way, and that our galaxy was so large it essentially constituted the entire universe. Curtis argued that the spiral nebulae were separate galaxies, distant island universes far beyond the Milky Way. The debate was not settled that night, but it framed the question clearly and set the stage for the discovery that would change everything. The breakthrough came a few years later, in 1924, when Edwin Hubble, working at the Mount Wilson Observatory in California, made a series of observations that resolved the debate once and for all. Using the most powerful telescope of the time, Hubble focused on the Andromeda Nebula, one of the largest and brightest of the spiral nebulae. Inside it, he identified individual stars, including a type of variable star called a Cepheid. Cepheids are special because their brightness pulses in a regular rhythm, and the period of the pulse is directly related to their true luminosity. By measuring the period, Hubble could calculate how bright the Cepheid really was, and by comparing that to how bright it appeared from Earth, he could calculate how far away it must be. The result was staggering. The Cepheid in Andromeda was so far away that Andromeda could not possibly be inside the Milky Way. It was at least 900,000 light-years away, far beyond the edges of our galaxy. Later measurements would revise this distance to about 2.5 million light-years, but the conclusion remained the same. Andromeda was not a nebula. It was a galaxy, a system of stars comparable in size to the Milky Way, but separated from us by an immense gulf of empty space. The spiral nebulae were not clouds. They were galaxies, island universes, each containing billions of stars. This discovery transformed astronomy overnight. The universe, which had been thought to consist only of the Milky Way, suddenly expanded to include countless other galaxies scattered across vast distances. Hubble continued his observations, measuring the distances to more and more galaxies, and in 1929 he made another groundbreaking discovery. The farther away a galaxy was, the faster it appeared to be moving away from us. This relationship, now known as Hubble's law, was the first evidence that the universe itself is expanding, that space is stretching, carrying galaxies apart. The implications were profound. If the universe is expanding now, it must have been smaller in the past, and if you trace that expansion backward far enough, you arrive at a moment when everything was compressed into a single point. This was the origin of the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding ever since. The Great Debate and Hubble's discoveries marked a turning point in human understanding. For the first time, we knew that the Milky Way was just one galaxy among many, and that the universe extended far beyond anything we had previously imagined. The scale of existence had expanded dramatically, and with it came new questions. How many galaxies are there? How far does the universe extend? And how does our galaxy, vast as it is, compare to the whole? The discovery also changed how we think about our place in the cosmos. Before Hubble, it was possible to imagine that the Milky Way was special, perhaps even unique, the center of everything. After Hubble, it became clear that we occupy no privileged position. The Milky Way is an ordinary spiral galaxy, one among hundreds of billions, perhaps trillions. We are not at the center. We are not unique. We are simply here, on one planet, in one star system, in one galaxy, in a universe filled with galaxies. This realization, though humbling, also connected us to something larger. We are part of a cosmic community, one member of a vast population of galaxies scattered across space. The Great Debate also reminds us that knowledge is not static. For centuries, the brightest minds debated the nature of the spiral nebulae, and both sides had reasonable arguments. It was only through careful observation, through the patient accumulation of data, through the development of new tools and techniques, that the truth emerged. This is how science works. Slowly, incrementally, building understanding step by step. The discovery that the universe is far larger than our galaxy was not a sudden flash of insight, but the result of decades of work by many astronomers, each contributing a piece to the larger puzzle. As we sit with this discovery, we can appreciate how recent it is. Less than a century ago, humanity did not know that other galaxies existed. The expansion of our cosmic perspective is a modern phenomenon, a product of the 20th century. We are among the first generations to know that the Milky Way is just one island in an ocean of galaxies, and that the universe stretches far beyond anything visible to the naked eye. This knowledge is a gift, a window into reality that was closed for all of human history until very recently. The Great Debate and its resolution set the foundation for everything that follows. To compare the size of the universe to the size of our galaxy, we first need to know that galaxies exist, that they are separate systems, and that the universe contains vast numbers of them. Hubble's discovery gave us that knowledge, and in doing so, it opened the door to deeper questions about scale, distance, and the structure of the cosmos. We are no longer asking if there are other galaxies. We are asking how many, how far, and how the Milky Way fits into the larger picture. And those are the questions we will continue to explore together, step by gentle step. When Edwin Hubble announced his findings in 1924, confirming that Andromeda was a separate galaxy far beyond the Milky Way, the response from the scientific community and the public alike was one of profound awe. It was not simply that the universe had grown larger in their minds, though it certainly had. It was that the expansion was so dramatic, so complete, that it required a fundamental rethinking of humanity's place in existence. The Milky Way, which had seemed to encompass everything, was suddenly revealed to be just one structure among countless others. The universe was not a single island, but an archipelago, and the scale of that archipelago was staggering. For astronomers, the discovery was both exhilarating and disorienting. On one hand, it validated decades of speculation and debate. Those who had argued for island universes were vindicated. The spiral nebulae were indeed distant galaxies, and the universe was far richer and more complex than anyone had dared to imagine. On the other hand, it meant that almost everything they thought they knew about the scale of the cosmos was wrong. The Milky Way, which many had believed to be synonymous with the universe itself, was revealed to be merely local, a neighbourhood in a much larger city. The sense of scale that astronomers had carefully built up over centuries collapsed and had to be rebuilt on a far grander foundation. The public response was equally powerful, though perhaps more emotional. Newspaper headlines proclaimed the discovery in bold letters, and popular magazines ran articles trying to explain what it meant. Writers and poets tried to capture the feeling in words, though many found language inadequate to the task. How do you describe the experience of learning that the universe is not just larger than you thought, but incomparably, unimaginably larger? Some responded with a sense of diminishment, feeling that humanity had been reduced to insignificance in a cosmos too vast to care about us. Others responded with wonder, feeling that the expansion of the universe expanded their own sense of possibility, that a cosmos with billions of galaxies was a cosmos rich with mystery and potential. There was also a philosophical dimension to the response. For centuries, humanity had placed itself at the centre of creation. Earth was the centre of the universe, then the Sun, then the Milky Way. Each shift outward had been resisted, and each had eventually been accepted, but always with the hope that we occupied some special position. Hubble's discovery made it clear that there was no centre, no privileged position. The Milky Way was one among many, and there was no reason to think it was special in any way. This was the final blow to anthropocentrism, the idea that humans or our home are somehow central to the cosmos. We are not central. We are peripheral. One planet among billions, one star among hundreds of billions, one galaxy among trillions. And yet, paradoxically, this realization also had a unifying effect. If we are not special, then neither is anyone else. Every galaxy, every star, every planet occupies the same status in the cosmos, a part of the whole, neither more nor less important than any other part. This levelling effect can be seen as either humbling or empowering, depending on perspective. On one hand, it reminds us that we are small, temporary, and not the focus of cosmic attention. On the other hand, it reminds us that we are part of a vast community of structures, connected by the same laws of physics, the same history of expansion, the same journey from the Big Bang to the present. The expansion of cosmic scale also had practical implications for astronomy. If galaxies existed beyond the Milky Way, then studying them could reveal information about the universe as a whole. Astronomers could no longer focus only on nearby stars and nebulae. They had to develop new techniques for observing distant galaxies, for measuring their distances, for understanding their properties. This led to a golden age of observational astronomy. As telescopes grew larger and more powerful, and as new technologies like photographic plates and spectroscopy allowed astronomers to capture and analyze light from ever more distant sources, Hubble himself continued to push the boundaries. Establishing that galaxies existed beyond the Milky Way, he set out to measure how far away they were and how fast they were moving. Using spectroscopy, he analyzed the light from distant galaxies and noticed something remarkable. The light was shifted toward the red end of the spectrum, a phenomenon known as redshift. The farther away a galaxy was, the more its light was redshifted. Hubble interpreted this as a Doppler effect, caused by the galaxy moving away from us. And the pattern he found was striking. The more distant a galaxy, the faster it appeared to be receding. This relationship, now known as Hubble's law, suggested that the universe itself was expanding, that space was stretching, carrying galaxies apart. This discovery amplified the sense of awe that had accompanied the realization that galaxies existed in the first place. Not only was the universe vast, but it was also dynamic. It was growing, changing, evolving. The cosmos was not a static backdrop against which events unfolded, but an active participant in the story. expanding outward from some ancient origin. This led directly to the development of the Big Bang theory, the idea that the universe began in a hot, dense state and has been expanding and cooling ever since. The expansion was not just a property of galaxies moving through space, but a property of space itself. The fabric of the cosmos was stretching, and galaxies were like dots on a balloon, carried apart as the balloon inflated. The sense of awe that accompanied these discoveries has never fully faded. Even today, more than a century later, astronomers and the public alike continue to marvel at the scale and dynamics of the universe. Every new telescope, every new observation, every new measurement adds to the picture, revealing more galaxies, more structure, more complexity. The James Webb Space Telescope, launched in 2021, has captured images of galaxies so distant that their light has been travelling for more than 13 billion years, showing us the universe as it was when it was less than a billion years old. These images are breathtaking, not just because they are beautiful, but because they represent a glimpse into deep time, a view of the cosmos in its youth. The first response to the discovery that the universe is far larger than our galaxy was awe, and that awe persists. It is an awe rooted in the recognition that we live in a cosmos that exceeds our ability to fully comprehend it, that stretches beyond our vision, that contains more galaxies than we can count and more stars than we can imagine. It is an awe that humbles us, reminding us of our smallness, but also elevates us, reminding us that we are capable of understanding, of measuring, of reaching out with telescopes and minds to grasp something far larger than ourselves. This awe is also what drives us forward. The discovery of galaxies beyond the Milky Way did not answer all questions. It opened new ones. How many galaxies are there? How are they distributed? What is their history? How did they form? And how does the Milky Way, our home galaxy, compare to the rest? These questions have shaped astronomy for the past century, and they continue to guide research today. The sense of expansion, of scale growing beyond previous limits, is not just a historical event but an ongoing process. Every year, our understanding of the universe expands, and with it, our sense of awe deepens. As we sit with this response, this mixture of humility and wonder, we can appreciate what it means to live in a time when such knowledge is available. For most of human history, the stars were mysteries, unreachable and unknowable. Today, we know not only that they are suns like our own, but that they are organized into galaxies, that those galaxies number in the trillions, and that the universe itself is expanding. This knowledge is extraordinary, and the response it evokes, this deep sense of awe, is entirely appropriate. We are small, yes, but we are also aware, and in that awareness lies something remarkable, something worth pausing to notice and appreciate. As astronomers absorbed the discovery that the universe extends far beyond the Milky Way, a new question emerged, one that seemed to contain a contradiction at its heart. Is the universe finite or infinite? On one hand, we can measure the observable universe, the part we can see. It stretches about 93 billion light-years across, a staggering but definite number. On the other hand, there is no reason to think that the universe stops at the edge of what we can observe. Space may continue beyond that horizon, perhaps indefinitely, perhaps infinitely. This tension between what we can measure and what might truly be has become one of the central puzzles in cosmology, a contradiction that challenges our intuitions and forces us to think carefully about the nature of existence itself. The observable universe is finite, by definition. It is defined by the age of the cosmos and the speed of light. Light travels at a finite speed, about 300,000 kilometers per second, and the universe has existed for a finite time, about 13.8 billion years. This means there is a limit to how far we can see. Light from regions more distant than the observable universe simply has not had time to reach us yet. The edge of the observable universe is not a physical boundary, not a wall or a barrier, but a horizon, the limit of what is accessible to our observations. Beyond that horizon, space likely continues, but we cannot see it, and we may never be able to. But here is where the contradiction arises. The observable universe is finite, but the universe itself may not be. There are two possibilities. The first is that the universe is finite, that it has a definite size and shape, perhaps wrapping around on itself like the surface of a sphere. In this case, if you could somehow travel far enough in one direction, you might eventually return to your starting point. Just as a traveller on Earth can circumnavigate the globe. The second possibility is that the universe is infinite, that space extends forever in all directions, with no edge and no boundary. In this case, the observable universe is just a bubble within an infinite expanse, and beyond our horizon lies more space, more galaxies, more structure, continuing without end. Current observations do not definitively answer which of these possibilities is true. Measurements of the universe's geometry suggest that it is very close to flat, which is consistent with both a finite universe that is extremely large and an infinite universe. The data allow for either possibility, though an infinite universe seems slightly more likely given the extreme flatness observed. But even if the universe is finite, it is so large that the difference between finite and infinite becomes almost philosophical. Whether the universe has an edge trillions of light years away or extends infinitely hardly matters for practical purposes, since we can never reach or observe those distant regions. This contradiction, finite in observation but possibly infinite in reality, reflects a deeper truth about the limits of knowledge. We are embedded within the universe, observing it from the inside, and our observations are constrained by the speed of light and the age of the cosmos. We can never step outside and see the universe as a whole. We can only see a portion of it, a bubble of light centered on us. This is true for every observer, everywhere in the universe. Each has their own observable universe, their own horizon, their own finite view of an expanse that may be infinite. The contradiction also touches on questions of time. The universe is 13.8 billion years old, a finite age. But will it exist forever? Or will it eventually end? Current evidence suggests that the universe will continue expanding indefinitely, driven by dark energy, a mysterious force that accelerates the expansion. In this scenario, the universe has no end. In time, only an endless future in which galaxies drift farther apart, stars burn out, and eventually, in the far, far future, even black holes evaporate through a process called Hawking radiation. This future, trillions of years away, is one of increasing cold, darkness, and isolation. But it is also infinite in duration. The universe, finite in age, may be infinite in lifespan. Another layer of the contradiction involves the difference between the physical universe and the observable universe. The physical universe is everything that exists, whether or not we can see it. The observable universe is the subset we can access with light and other signals. Because the universe is expanding, and because that expansion is accelerating, there are galaxies that we can see now whose light, emitted today, will never reach us in the future. These galaxies are receding from us faster than light can travel, not because they are moving through space faster than light, but because space itself is expanding between us and them. As a result, they are crossing an event horizon, disappearing from view, becoming permanently inaccessible. The observable universe, in this sense, is shrinking even as the physical universe grows. This creates a strange situation where the universe is both expanding and contracting, depending on which aspect you focus on. The physical universe is expanding, growing larger with every passing second, but the observable universe, the part we can ever hope to see, is in some sense shrinking, as more and more galaxies slip beyond the event horizon, carried away by the accelerating expansion. The contradiction is built into the structure of the cosmos itself, a feature of living in an expanding universe where the speed of light is finite. The tension between finite and infinite also appears in mathematics. Infinity is a concept, not a number. It represents something without bound, without end. But we cannot measure infinity directly. We can only measure finite quantities and extrapolate. When astronomers say the universe might be infinite, they are saying that their measurements are consistent with that possibility, not that they have measured infinity itself. The universe might also be finite, but so large that it appears infinite on any scale we can observe. The distinction may ultimately be beyond our capacity to resolve, a question that hovers at the edge of what science can answer. Philosophically, the contradiction between finite and infinite raises questions about meaning. If the universe is infinite, does that make our finite lives more or less significant? Some argue that in an infinite universe, everything that can happen will happen, somewhere, making any particular event less unique. Others argue that infinity makes each event more precious, because even though the universe is vast, this moment, this experience, this life is still singular. The contradiction does not resolve into a clear answer, but it invites reflection, a gentle pondering of what it means to be finite within something that may be infinite. The contradiction is also a reminder of the limits of language. Words like finite and infinite are useful, but they are also abstractions, attempts to capture something that exceeds direct experience. We cannot picture infinity. We cannot fully grasp what it means for space to extend without end. And yet, we can reason about it, describe it mathematically, and consider its implications. The contradiction is not a failure of understanding, but an indication of how far our minds can reach, stretching toward concepts that lie beyond everyday intuition. As we sit with this contradiction, it becomes less troubling and more intriguing. The universe is finite in what we can see, but possibly infinite in what exists. It is finite in age, but infinite in duration. It is expanding in physical size, but shrinking in observable scope. Each of these seeming contradictions reflects a truth about the cosmos, a truth that challenges simple categories and invites us to think more deeply. The universe does not owe us simplicity. It offers complexity, nuance, and mystery. And in that mystery lies much of its beauty. The contradiction between finite and infinite also connects to the question we are exploring tonight. How big is the universe compared to our galaxy? The Milky Way is finite, clearly so, with a definite size and structure. The universe, by contrast, may be infinite, or it may merely be so large that the difference hardly matters. Either way, the comparison reveals a gulf so vast that it challenges comprehension. Our galaxy is one island in an ocean that may have no shore. And whether that ocean is finite or infinite, the scale is overwhelming, humbling, and awe-inspiring all at once. To compare the size of the universe to the size of our galaxy, we need to measure both. But how do you measure something as vast as a galaxy, let alone something as incomprehensibly large as the universe? The challenge is not just practical but conceptual. We cannot lay a ruler across the Milky Way or stretch a tape measure to distant galaxies. We cannot travel to the edge of the observable universe to check how far it extends. Instead, we must use indirect methods, clever techniques that turn light into distance, motion into measurement, and patterns into maps. Tonight, we will walk through some of the theories and methods astronomers use to measure the immeasurable, building a ladder of techniques that reaches from nearby stars to the farthest galaxies. The first step is to understand what distance means in space. On Earth, distance is straightforward. You can walk from one place to another, count the steps, measure the time, and calculate the distance. But in space, objects are so far away that direct measurement is impossible. Instead, astronomers use light as their primary tool. Light travels at a known constant speed, and by measuring how long it takes light to travel from an object to us, or by measuring how faint or bright an object appears, we can infer its distance. This transforms the problem from one of physical measurement to one of observation and calculation. The foundation of cosmic measurement is parallax, the apparent shift in position of a nearby object against a more distant background when viewed from two different locations. You can demonstrate parallax yourself by holding your finger in front of your face and closing one eye, then the other. Your finger appears to jump relative to the background. Astronomers use the same principle, but instead of using two eyes, they use Earth's position at two different times of year, when our planet is on opposite sides of its orbit around the Sunday. This creates a baseline of about 300 million kilometers, and by measuring the tiny shift in a nearby star's position, astronomers can calculate its distance using simple trigonometry. Parallax works beautifully for nearby stars, within a few hundred light years. But beyond that, the angles become too small to measure accurately, even with the most precise instruments. For farther distances, astronomers need a different technique. This is where standard candles come in, objects whose intrinsic brightness is known. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate how far away it must be. The farther away an object is, the fainter it appears, following a precise mathematical relationship called the inverse square law. One of the most important standard candles is a type of star called a Cepheid variable. Cepheids are pulsating stars, whose brightness changes in a regular, predictable rhythm. The period of the pulsation, how long it takes to go from bright to dim and back again, is directly related to the star's true luminosity. By measuring the period, astronomers know how bright the Cepheid really is. By measuring how bright it appears, they can calculate its distance. This method, refined by Henrietta Swan Leavitt in the early 1900s, was the key to Edwin Hubble's discovery that Andromeda is a separate galaxy. He identified Cepheids in Andromeda, measured their periods and apparent brightness, and calculated the distance, revealing that Andromeda was far beyond the Milky Way. Cepheids can be seen in galaxies up to about 100 million light-years away, but beyond that, even they become too faint. For even greater distances, astronomers use another standard candle, type Ia supernovae. These are exploding stars, white dwarfs that have accumulated matter from a companion star until they reach a critical mass and detonate in a thermonuclear explosion. Because the mass at which this happens is always roughly the same, type Ia supernovae always reach roughly the same peak brightness, making them excellent standard candles. They are so bright that they can be seen across billions of light years, allowing astronomers to measure distances to galaxies far across the universe. Beyond supernovae, the method shifts again, this time relying on the expansion of the universe itself. As space expands, it stretches the light travelling through it, shifting it toward longer wavelengths, toward the red end of the spectrum. This redshift is proportional to distance. The farther away a galaxy is, the more its light is redshifted. By measuring the redshift of a galaxy's light and applying Hubble's law, astronomers can estimate its distance. This method works for galaxies billions of light-years away, reaching back to when the universe was young. Redshift has become one of the primary tools for mapping the large-scale structure of the cosmos. Each of these methods, parallax, Cepheids, supernovae, redshift, forms a rung on what astronomers call the cosmic distance ladder. Each rung reaches farther than the last, and each relies on calibrations from the rung below. Parallax calibrates Cepheids, Cepheids calibrate supernovae, and supernovae calibrate redshift. The ladder is a chain of interdependent techniques, each extending our reach deeper into space. But the ladder also has uncertainties that accumulate with each step. Errors in parallax measurements propagate into Cepheid distances, which propagate into supernova distances, and so on. This is why measuring cosmic distances is both an art and a science, requiring careful calibration, cross-checking, and refinement. Another method involves gravitational lensing, where the gravity of a massive object, like a galaxy or cluster, bends the light from a more distant object, creating distorted images or even multiple images. By analysing the lensing effect, astronomers can infer the mass of the foreground object and the distance to the background object. This method does not rely on standard candles and provides an independent check on other distance measurements. It has become increasingly important as telescopes have grown more powerful and lensing events more common in observations. The cosmic distance ladder is not perfect. There are debates about the exact values of key measurements, such as the Hubble constant, which describes the rate of the universe's expansion. Different methods sometimes give slightly different results, leading to what astronomers call the Hubble tension, a discrepancy between measurements of the expansion rate from the early universe and measurements from the late universe. Resolving this tension is one of the major challenges in cosmology today, and it may require new physics or refinements to existing techniques. But despite these uncertainties, the distance ladder has been remarkably successful, allowing us to map the universe from our solar system to the edges of the observable cosmos. Measuring the immeasurable is not just about numbers, it is about creativity, about finding ways to turn faint signals into profound knowledge. It is about building chains of inference where each step rests on the one before, and each step extends our reach farther into the unknown. It is about patience as generations of astronomers refine techniques, improve instruments, and slowly, incrementally, construct a map of the cosmos. And it is about humility, recognizing that every measurement comes with uncertainty, that every map is incomplete, and that the universe will always hold mysteries beyond our current reach. As we sit with these methods, we can appreciate the ingenuity behind them. To measure the distance to a star by observing its tiny shift in position, to measure the distance to a galaxy by identifying a pulsating star and timing its rhythm, to measure the distance to the farthest galaxies by analysing the stretching of their light. Each method is a triumph of human creativity, a way of reaching across the void with nothing but light and mathematics. And together, they allow us to answer questions that once seemed unanswerable, to compare scales that once seemed incomparable, to measure the immeasurable, and in doing so, to glimpse the true size of the universe. The cosmic distance ladder is not a single tool but a sequence of techniques, each building on the previous one, each extending our reach farther into the universe. It is called a ladder because you must climb it step by step, using the lower rungs to establish the higher ones, gradually ascending from measurements of nearby stars to estimates of distances billions of light years away. Tonight, we will climb this ladder slowly, pausing at each rung to understand how it works, how it connects to the rungs above and below, and how together they allow us to map the cosmos from our galactic neighbourhood to the farthest reaches of observable space. The first rung is the most direct, radar ranging. For objects within our solar system, we can bounce radio waves off them and measure how long it takes for the signal to return. Since radio waves travel at the speed of light, we can calculate the distance precisely. This method works for planets, moons, and asteroids, giving us exact measurements within our local cosmic neighbourhood. Radar ranging established the astronomical unit, the distance from Earth to the Sun, which is about 150 million kilometres. This distance became the baseline for all further measurements, the first step that anchors the entire ladder. The second rung is parallax, which we discussed earlier. By observing a nearby star from two positions in Earth's orbit 6 months apart, astronomers can measure the tiny angular shift and calculate the star's distance. For the nearest stars, this method is remarkably accurate. The European Space Agency's Gaia mission has measured parallaxes for more than 1 billion stars, creating a three-dimensional map of the Milky Way with unprecedented precision. Parallax establishes distances out to several thousand light years, but beyond that, the angles become too small to measure reliably, and we need the next rung. The third rung involves main sequence fitting, a technique that uses our understanding of stellar physics. Stars of a given mass and composition fall along a predictable relationship between their temperature and brightness. called the main sequence. By observing a cluster of stars and comparing their apparent brightnesses to their expected intrinsic brightnesses, astronomers can estimate the distance to the cluster. This method works because all stars in a cluster are roughly the same distance from us, so their relative brightnesses reveal their intrinsic properties. Main sequence fitting extends our reach to tens of thousands of light years, bringing distant parts of the Milky Way into measurable range. The fourth rung is Cepheid variables, the pulsating stars discovered by Henrietta Swan Leavitt. Leavitt was working at the Harvard College Observatory in the early 1900s, analysing photographic plates of the Magellanic Clouds, two small galaxies that orbit the Milky Way. She noticed that some stars in these clouds varied in brightness, with regular periods, and she discovered a relationship. The longer the period, the brighter the star. This period luminosity relationship meant that by measuring how long it took a Cepheid to pulse, she could determine its true brightness. And knowing its true brightness, she could calculate its distance by comparing it to its apparent brightness. Cepheids became the key to measuring distances beyond the Milky Way. Edwin Hubble used them to determine that Andromeda was a separate galaxy, and astronomers have used them ever since to map the local universe. Cepheids can be detected in galaxies up to about 100 million light-years away, making them invaluable for calibrating the next rungs of the ladder. But they require powerful telescopes to see at such distances, and beyond 100 million light-years, even Cepheids fade into the background, too faint to identify clearly. The fifth rung is Type Ia supernovae, the thermonuclear explosions of white dwarf stars. These supernovae are not only incredibly bright, they are also remarkably consistent in their peak brightness, making them excellent standard candles. When a white dwarf in a binary system accumulates enough matter from a companion star, it reaches a critical mass called the Chandrasekhar limit, about 1.4 times the mass of the Sunday. At this point, the white dwarf collapses and rebounds in a runaway fusion reaction, exploding with roughly the same energy every time. Because the physics is consistent, the peak brightness is consistent, and astronomers can use these explosions as distance markers across billions of light years. Type Ia supernovae were used in the 1,990 seconds to make one of the most important discoveries in cosmology. The universe's expansion is accelerating. Two teams of astronomers independently measured distances to distant supernovae and compared them to their redshifts, expecting to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. Distant supernovae were farther away than expected, indicating that the expansion was speeding up, driven by a mysterious force now called dark energy. This discovery earned the Nobel Prize in Physics in 2011 and reshaped our understanding of the universe's fate. The sixth rung relies on redshift and Hubble's law. As the universe expands, space itself stretches, and light travelling through that space is stretched as well, shifting toward longer, redder wavelengths. The farther away a galaxy is, the more space is expanded during the light's journey, and the more redshifted the light becomes. By measuring the redshift of a galaxy's spectrum, astronomers can estimate its distance using the relationship Hubble discovered. Distance is proportional to redshift. This method works for galaxies billions of light years away, reaching back to when the universe was only a few 100 million years old. Redshift is not a perfect distance indicator because it relies on assumptions about the universe's expansion history, which is influenced by the density of matter and dark energy. Different models of the universe's composition give slightly different distance estimates for the same redshift. But by combining redshift measurements with other techniques, and by carefully modelling the universe's expansion, astronomers can estimate distances to the farthest observable galaxies with reasonable confidence. The seventh and highest rung involves the cosmic microwave background, the faint afterglow of the Big Bang. This radiation comes from a time when the universe was only 380,000 years old, when it had cooled enough for atoms to form and light to travel freely. The cosmic microwave background is nearly uniform, but it contains tiny temperature fluctuations that reveal information about the universe's composition, geometry, and expansion history. By analyzing these fluctuations, astronomers can calibrate the entire distance ladder, checking whether the measurements at each rung are consistent with the overall picture of the universe. Climbing the cosmic distance ladder is an exercise in both precision and uncertainty. Each rung builds on the previous one, so errors accumulate as you climb higher. If the parallax measurements are slightly off, the Cepheid distances will be slightly off, the supernova distances will be slightly off, and the redshift calibrations will be slightly off. This is why astronomers constantly work to improve measurements at each level, refining techniques, cross-checking results, and searching for independent methods to verify distances. The ladder is strong, but it is not perfect, and understanding its limitations is as important as understanding its power. One of the challenges is that different rungs sometimes give slightly different answers. The Hubble constant, which describes the rate of the universe's expansion, can be measured using Cepheids and supernovae in nearby galaxies, or it can be inferred from the cosmic microwave background. These two methods currently give results that differ by a few percent, a discrepancy known as the Hubble tension. This may indicate a problem with one of the measurement techniques, or it may hint at new physics, something we do not yet understand about the universe's expansion or composition. Resolving this tension is one of the major goals of modern cosmology. Another challenge is that the ladder only reaches so far. The farthest galaxies we can see are so distant that their light has been travelling for more than 13 billion years, showing us the universe as it was in its infancy. Beyond that, there are no galaxies to observe, only the cosmic microwave background. We cannot climb higher than that rung because there is no light from earlier times. The universe before 380,000 years old was opaque, filled with hot plasma that scattered light, making it impossible to see through. The cosmic distance ladder ends there, at the edge of the observable universe, beyond which we can only infer and imagine. Despite these challenges, the cosmic distance ladder is one of the great achievements of astronomy. It represents centuries of work by countless astronomers, each contributing a technique, a refinement, a measurement. It is a testament to human ingenuity, to the ability to take faint signals from distant sources and turn them into knowledge about the structure and scale of the cosmos. And it is the tool that allows us to answer the question we are exploring tonight. How big is the universe compared to our galaxy? Without the distance ladder, we could not measure either. With it, we can map both and compare them, tracing the scale from the local to the cosmic. As we climb down from the ladder and return to our starting point, we can appreciate what it has shown us. The universe is not a mystery beyond all measurement. It is a place we can map, a structure we can understand, a scale we can describe. The ladder is a bridge between the immediate and the five, infinite, between the stars we can touch with telescopes and the galaxies we can barely glimpse at the edge of light. It is the path that leads from the Milky Way, our home, to the universe, our context. And by climbing it, step by patient step, we transform the immeasurable into something we can hold, gently, in our minds. Now that we understand how distances are measured, we can turn to the data itself, the actual numbers that describe the scale of the Milky Way and the universe. These numbers are large, almost absurdly so, and they resist intuition. But tonight, we will present them gently, without rushing, letting each one settle before moving to the next. We will build a picture not through memorization but through gradual accumulation, allowing the scale to reveal itself layer by layer until the comparison between galaxy and universe becomes clear. Let us begin with the Milky Way. Our galaxy is a barred spiral, a flattened disk with sweeping arms and a central bulge. The disk is about 100,000 light-years across, which means light takes 100,000 years to travel from one side to the other. To put that in more familiar units, it is about 946 trillion kilometers, or roughly 587 trillion miles. These numbers are so large, they cease to have meaning in everyday terms. No human can visualize 1,000,000,000,000 of anything, let alone nearly 1,000,000,000,000,000. But we can say this: if you could travel at the speed of light, the fastest speed possible, it would still take 100,000 years to cross the Milky Way. That is longer than recorded human history, longer than modern humans have existed as a species. The Milky Way's thickness is much smaller, only about 1,000 light-years in the disk and a few thousand in the bulge. This makes the galaxy extremely flat, like a dinner plate or a coin. If you scaled the Milky Way down so that its width was 1 meter, its thickness would be only about 1 centimeter. This flatness is a result of rotation, as the galaxy formed from a collapsing cloud of gas. Rotation caused the material to flatten into a disk, just as spinning pizza dough flattens into a round shape. The flatness is not just a visual feature, but a consequence of the physics of angular momentum and gravity. Within this disk are between 200 and 400 billion stars. The uncertainty in this number is large because many stars are too faint to see directly, hidden behind dust clouds, or simply too dim to detect with current telescopes. The lower estimate, 200 billion, is conservative. The higher estimate, 400 billion, accounts for vast numbers of small, faint red dwarf stars that are difficult to observe but likely numerous. Either way, the number is staggering. If every star were a grain of sand, 200 billion grains would fill several dump trucks. 400 billion would fill a small building. And each of those grains represents an entire sun, many with planets, some perhaps with moons, atmospheres, and even conditions suitable for life. The total mass of the Milky Way is even more impressive, but much of it is not in stars. The visible matter, stars, gas, and dust accounts for only about 10–15% of the galaxy's total mass. The rest is dark matter, an invisible substance that does not emit, absorb, or reflect light, but makes its presence known through gravity. Dark matter forms a halo around the Milky Way, extending far beyond the visible disk, perhaps 300,000 light-years or more from the center. When astronomers include this dark matter halo, the total mass of the Milky Way is estimated at about 1 to 1.5 trillion times the mass of the Sunday. This includes everything: stars, planets, gas, dust, black holes, and the vast unseen reservoir of dark matter that holds it all together. Now let us turn to the universe. The observable universe, the part we can see, has a radius of about 46.5 billion light-years. This gives it a diameter of about 93 billion light-years, or roughly 880 trillion kilometers. This number is so large, it almost loses meaning. If the Milky Way is difficult to comprehend, the observable universe is exponentially more so. But here is one way to think about it. The observable universe is about 930,000 times wider than the Milky Way. If you could shrink the Milky Way down to the size of a coin, the observable universe would be the size of the continental United States. The scale difference is immense, almost incomprehensible, and yet it is real, supported by measurements and observations. One question often arises: if the universe is only 13.8 billion years old, how can the observable universe be 93 billion light-years across? Shouldn't light have only travelled 13.8 billion light-years in that time? The answer lies in the expansion of space. When light left a distant galaxy 13 billion years ago, the galaxy was much closer than it is now. As the light travelled, space expanded, stretching the distance between us and the galaxy. By the time the light reaches us, the galaxy is no longer where it was when the light left. It has been carried away by the expansion of space. So the farthest galaxies we can see are now about 46.5 billion light-years away, even though their light has been travelling for less than 14 billion years. Within the observable universe, astronomers estimate there are about 2 trillion galaxies. This number is based on deep surveys of the sky, where telescopes observe tiny patches of space and count the galaxies within them, then extrapolate across the entire sky. Each of these galaxies contains, on average, hundreds of billions of stars, though some have fewer and some have more. If we take a conservative average of 100 billion stars per galaxy, the total number of stars in the observable universe is about 200 sextillion, or 2 followed by 23 zeros. 200 sextillion. This is a number so large it defies visualization. If every star were a grain of sand, there would be enough to cover every beach on Earth many times over. But even these numbers are incomplete. The observable universe is just the part we can see. Beyond the horizon of observation, space likely continues, perhaps indefinitely. If the universe is infinite, then the total number of galaxies is infinite, and the total number of stars is infinite. The observable universe is just a bubble, a finite sample of something that may have no edge. This is both humbling and awe-inspiring. No matter how far we can see, there may always be more, an endless expanse of galaxies stretching beyond the reach of light. The mass-energy content of the observable universe is another staggering figure. Ordinary matter, the atoms that make up stars, planets, and us, accounts for only about 5% of the total. Dark matter, invisible but gravitationally influential, makes up about 27%. The remaining 68% is dark energy, the mysterious force driving the accelerated expansion of the universe. The total mass energy of the observable universe is estimated at about 1053 kilograms, a number so large it becomes abstract. For comparison, the Earth has a mass of about 6 × 10^24 kilograms, which means the observable universe is about 10^28 times more massive than Earth, or 10 octillion times heavier. When we compare the Milky Way to the observable universe, the difference is stark. In volume, the observable universe is about 10^18 times larger than the Milky Way, or a billion times larger. In mass, the observable universe is roughly 10^11 times more massive, or about 100 billion times heavier, though this comparison is complicated by dark energy, which does not clump into galaxies. In number of stars, the observable universe contains roughly 1,000,000 times more stars than the Milky Way, if we account for the 2 trillion galaxies and their average stellar populations. These numbers are not just abstract statistics. They represent real structures, real distances, real masses. Every galaxy in the observable universe is a place, a collection of stars, potential home for planets, and perhaps life. Every star is a sun, shining with nuclear fire, warming any worlds that orbit it. Every light year is a distance that light travels, a span of space through which matter and energy move. The numbers are large, yes, but they describe a universe that is not empty but full, not barren but rich, not simple but complex. As we sit with these numbers, we can let go of the need to grasp them fully. It is enough to know that they are large, that the universe is vastly larger than the Milky Way, and that both are structures of extraordinary scale. The data is not meant to be memorized but felt, absorbed, allowed to reshape our sense of proportion. When we look at the night sky, we are looking at one galaxy among trillions. When we think about the stars, we are thinking about hundreds of billions in our galaxy alone, and sextillions across the universe. The data is a window into scale, and through that window, we glimpse the true size of existence. As we absorb the numbers, as we let the scale of the observable universe settle into our understanding, a deeper question emerges, one that shifts the conversation from what we can measure to what we cannot. We have established that the observable universe is about 93 billion light-years across, that it contains roughly 2 trillion galaxies, and that it is vastly, almost incomprehensibly larger than the Milky Way. But the observable universe is just that, observable. It is the part of the universe that light has had time to reach us from since the Big Bang. It is not necessarily the whole universe. It is simply the part we can see. And beyond that horizon, beyond the reach of our telescopes and our measurements, lies a deeper mystery. What lies beyond the observable universe? The honest answer is that we do not know, and we may never know. The edge of the observable universe is not a physical boundary but a horizon of light and time. Beyond it, there is almost certainly more space, more galaxies, more structure, but we cannot see it because the light from those regions has not had time to reach us yet. And because the universe is expanding, and that expansion is accelerating, there are regions of space that are receding from us so quickly that their light will never reach us, no matter how long we wait. They are beyond a horizon called the cosmic event horizon, and they are permanently inaccessible. This leads to a profound realization: the observable universe is not the universe. It is a bubble of light centered on us, a sphere of space from which signals can reach us. Every observer, everywhere in the universe, has their own observable universe, their own bubble of light. Someone in a galaxy 10 billion light-years away would see a different observable universe, one that overlaps with ours but extends in different directions. The full universe, the true totality of existence, may be far larger than any single observable bubble. It may even be infinite. If the universe is infinite, then the implications are staggering. An infinite universe would contain an infinite number of galaxies, an infinite number of stars, an infinite number of planets. Every possible configuration of matter would occur somewhere, not just once but infinitely many times. There would be other galaxies like the Milky Way, other solar systems like ours, other planets like Earth. In an infinite universe, everything that can happen does happen. Somewhere, infinitely often. This is both exhilarating and deeply strange, challenging our sense of uniqueness and identity. But is the universe infinite? The answer depends on its geometry. If the universe is flat, extending in all directions without curvature, then it is likely infinite, or at least so large that the difference between finite and infinite is beyond our ability to measure. If the universe is closed, curving back on itself like the surface of a sphere, then it is finite, with a definite size and volume, even if that size is unimaginably large. Current measurements of the cosmic microwave background suggest that the universe is very close to flat. So close that we cannot determine with certainty whether it is exactly flat or just nearly flat. This leaves both possibilities open. The universe might be infinite, or it might be finite, but so large that it appears flat on any scale we can observe. Even if the universe is finite, it is almost certainly far larger than the observable universe. Think of it this way. The observable universe is defined by the age of the cosmos and the speed of light. We can only see as far as light has had time to travel, but there is no reason to think the universe stops at that distance. Space likely continues beyond what we can observe, filled with more galaxies, more structure, more of the same patterns we see within the observable horizon. If the universe is finite, its total size might be 10 times larger than the observable universe, or 100 times, or 1,000. We simply do not know, and current technology does not allow us to find out. This uncertainty about what lies beyond is one of the deepest mysteries in cosmology. It is not a mystery we can solve with better telescopes or more precise measurements, because the limitation is fundamental. Light travels at a finite speed, and the universe has existed for a finite time. No matter how advanced our technology becomes, we can never see beyond the cosmic horizon. We can only infer, speculate, and imagine. This is both frustrating and humbling. Frustrating because we are limited, because there are questions we cannot answer with observation. Humbling because it reminds us that the universe is larger than our capacity to know it, that there are boundaries to knowledge built into the structure of reality itself. Another layer of the mystery involves the ultimate fate of the universe. If the expansion continues to accelerate, as current evidence suggests, then the observable universe will actually shrink over time, even as the physical universe grows. Galaxies beyond a certain distance are already receding faster than light, carried away by the expansion of space. Over billions of years, more and more galaxies will cross this threshold, disappearing from view, their light stretched beyond detection. In the far future, Perhaps 100 billion years from now, observers in the Milky Way, or what remains of it after merging with Andromeda, will see only the galaxies of the local group. Everything else will have vanished beyond the horizon, leaving a universe that appears small, dark, and empty. This raises a poignant thought. We live at a special time in cosmic history, a time when the universe is transparent, when galaxies are visible across vast distances, when the cosmic microwave background can still be detected. Future civilizations, if they exist, will not have access to the same evidence we do. They will not see the cosmic web, will not observe distant galaxies, will not be able to reconstruct the history of the universe from light. The knowledge we have now, the data we collect, the measurements we make, are in a sense time-limited. We are fortunate to live in an epoch when the universe still reveals its story. The mystery of what lies beyond also connects to questions about the origin of the universe. If the observable universe is just a small part of a much larger whole, then the Big Bang may not have been a single event, but a local phase transition, a region of space that began expanding rapidly, while other regions remained unchanged or expanded differently. Some theories, like eternal inflation, suggest that the universe is constantly creating new regions of space, new bubbles of expansion, each with its own properties. In this view, the observable universe is just one bubble among infinitely many, each separated from the others by vast expanses of still inflating space. We cannot observe these other bubbles, but they may exist, each a universe unto itself. These ideas are speculative, but they remind us that the mystery of what lies beyond is not just about distance. It is about the nature of reality, about whether the universe is finite or infinite, unique or part of a larger multiverse, knowable or fundamentally mysterious. The question challenges the limits of science, pushing us to consider what can and cannot be observed, what can and cannot be tested. And in that challenge lies much of the beauty of cosmology. It is a field that reaches toward the horizon of knowledge and acknowledges, with humility, that some things may lie forever beyond reach. As we sit with this mystery, we can let go of the need to resolve it. The universe may be infinite, or it may be finite but unimaginably large. What lies beyond the observable horizon may be more of the same, or it may be something entirely different. We do not know, and that is acceptable. The mystery is not a failure of science, but a reminder of the universe's depth, its refusal to be fully contained by our models and measurements. To ask what lies beyond is to stand at the edge of knowledge and look outward, knowing that the darkness holds more than we can ever see, but also knowing that the act of looking, of wondering, of asking, is itself meaningful. There comes a moment in understanding cosmic scale when something shifts inside. It is not just that you learn new facts or absorb new numbers. It is that your entire sense of proportion changes, your relationship to size and significance recalibrates, and the universe stops being an abstraction and becomes a context, a framework within which your life unfolds. This moment is different for everyone. For some, it comes when they first see images from the Hubble Deep Field, thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length. For others, it comes when they learn that the Milky Way is just one among trillions, or when they realize that most of the universe is already beyond reach, carried away by expansion. Tonight, let us explore this turning point, this shift in perspective that transforms how we see ourselves and our place in the cosmos. The shift often begins with a feeling of smallness. When you learn that the Milky Way is 100,000 light-years across, and that the universe is nearly 1,000,000 times larger, the immediate response can be a sense of diminishment. You are tiny, not just compared to the galaxy, but compared to the universe as a whole. Your life is brief, not just measured against the age of stars, but against the 13.8 billion years of cosmic history. Your concerns, your struggles, your ambitions, all of them shrink when placed against the backdrop of trillions of galaxies scattered across billions of light-years. This smallness can feel overwhelming, as though you have been rendered insignificant by the sheer scale of everything around you. But then, if you sit with it long enough, the feeling begins to change. Smallness does not have to mean insignificance. You are small, yes, but you are also aware. You are part of the universe, not separate from it. The atoms in your body were forged in stars, scattered by supernovae, gathered by gravity into a planet, and assembled over billions of years into the form you now inhabit. You are made of the universe, and in you, the universe has become conscious, capable of reflecting on its own scale and structure. Smallness, in this light, becomes a form of belonging. You are not diminished by the universe's size. You are included in it, woven into it, inseparable from it. This shift from smallness to belonging is the turning point. It is the moment when cosmic scale stops being oppressive and becomes liberating. You do not need to be large to matter. You do not need to be eternal to have significance. You matter because you are here, because you are aware, because you are capable of asking questions about the universe and understanding, even if only partially, the answers. The universe does not care about you in the sense of intentional design, but you care about the universe, and that caring is enough to create meaning. Another aspect of the shift involves time. When you learn that the universe is 13.8 billion years old, and that the light from distant galaxies has been travelling for billions of years to reach you, time ceases to be just a measure of days and years. It becomes a dimension of existence, a framework within which events unfold across unimaginable durations. The stars you see at night are not as they are now, but as they were when their light left them, years or centuries or millennia ago. The galaxies imaged by telescopes are not contemporary but historical, snapshots of the universe in its youth. Looking outward is looking backward, and the deeper you look, the farther back in time you see, until you reach the cosmic microwave background, the afterglow of the Big Bang, the oldest light in existence. This temporal dimension adds depth to the spatial scale. The universe is not just vast in space, but vast in time, and the two are interwoven, inseparable. To know this is to feel connected not only to distant places but to deep history, to understand that you are part of a story that has been unfolding for billions of years and will continue for billions more. Your life is a moment in that story, brief but real, fleeting but meaningful. The shift is from seeing time as a constraint to seeing it as a context, from feeling rushed by its passage to feeling held by its vastness. The shift also changes how you think about connection. Before understanding cosmic scale, it is easy to see yourself as isolated, separate from the rest of existence. But when you learn that the Milky Way is part of the local group, which is part of the Virgo supercluster, which is part of Laniakea, which is part of the cosmic web, you realize that separation is an illusion. Everything is connected, not just metaphorically but physically, through gravity, through the expansion of space, through the shared history of the Big Bang. The galaxies you see in the night sky are not strangers but neighbors, members of the same cosmic community, participants in the same unfolding story. This sense of connection extends to other people as well. Every human, regardless of where they live or what they believe, shares the same cosmic address. We are all on Earth, in the solar system, in the Milky Way, in the observable universe. The boundaries we draw between nations, cultures, and identities are real in human terms, but they are arbitrary compared to the natural boundaries of galaxies and superclusters. The shift is from seeing humanity as divided to seeing it as united. From focusing on what separates us to recognizing what we share. We are all, together, inhabitants of a small planet in a vast universe, and that shared situation creates a bond deeper than any difference. The turning point also involves acceptance. Before the shift, the vastness of the universe can feel like a problem, something that needs to be solved or reconciled. How can life have meaning in a universe so large? How can individual experiences matter when set against such scale? But after the shift, these questions lose their urgency. The universe does not owe us meaning. We create meaning through awareness, through relationship, through the simple act of being present. The vastness does not diminish meaning. It provides a context within which meaning arises, a stage on which the drama of consciousness unfolds. One of the most profound aspects of the shift is realizing that the universe's size is not a barrier but an invitation. The fact that there are trillions of galaxies, each with billions of stars, each potentially with planets and moons and atmospheres, means that the universe is not empty but full, not barren but rich, not simple but complex. Every galaxy is a place, a structure, a system. Every star is a sun, potentially warming worlds. The vastness is not a void, but a landscape, a terrain filled with possibility, with stories, with potential for discovery. To learn about cosmic scale is to learn that we live in a universe of abundance, where the sheer number of objects guarantees that interesting, beautiful, surprising things are happening everywhere, all the time. The shift in perspective is not something that happens all at once. It unfolds gradually, deepening with each new piece of knowledge, each new observation, each quiet moment of reflection. It is a shift that can be revisited, a perspective that can be refreshed, a way of seeing that becomes easier with practice. And once it happens, it changes how you move through the world. Problems feel smaller, not because they are less real, but because they are contextualized. Worries lose some of their weight. The urgency of the moment softens. You carry with you a sense of the vastness, a reminder that you are part of something larger, and that reminder provides a kind of peace. This is the turning point, the moment when cosmic scale stops being overwhelming and starts being grounding, when smallness becomes belonging, when vastness becomes context, and when the universe stops being out there and becomes right here, around you, within you, inseparable from your existence. This shift is the deepest gift that understanding cosmic scale can offer, and it is available to anyone willing to stand beneath the stars, look upward, and let the immensity wash over them until it transforms into something gentler, something like home. One of the most beautiful consequences of understanding cosmic scale is realizing that when we look outward into space, we are also looking backward in time. Light travels at a finite speed, about 300,000 kilometers per second, and though that is extraordinarily fast by human standards, it is not instantaneous. Every photon that reaches your eye has been traveling for some amount of time, carrying with it not just information about where it came from, but when it left. The farther away an object is, the longer its light has been traveling, and the farther back in time we see. In this way, telescopes become time machines, allowing us to observe not just distant places but distant epochs, not just far galaxies but ancient galaxies, the universe as it was billions of years ago. This concept is easier to grasp when we start close to home. When you look at the moon, you see it as it was about 1.3 seconds ago, the time it takes light to travel the 384,000 kilometers between the moon and Earth. The delay is so brief it is imperceptible, but it is real. If the sun were to suddenly vanish, we would not know it for 8 minutes, because the light from the moment of its disappearance would still be travelling toward us. The sun we see is always slightly in the past, a ghost of where it was when the light began its journey. The nearest star system, Alpha Centauri, is about 4.4 light-years away. When you see Alpha Centauri in the night sky, you are seeing it as it was 4.4 years ago. If something dramatic happened there today, a planet colliding with the star, or the star suddenly brightening, we would not know about it until 4.4 years from now. The delay grows with distance. A star 100 light-years away shows us what it looked like a century ago, when our great-grandparents were young. A star 1,000 light-years away shows us the medieval period. A star 10,000 light-years away shows us the end of the last ice age. Every star in the night sky is a time capsule, its light carrying a message from the past. When we extend this principle to galaxies, the effect becomes profound. Andromeda, our nearest large galactic neighbour, is about 2.5 million light-years away. The light we see from Andromeda tonight left that galaxy 2.5 million years ago, long before humans existed, when our ancestors were still primitive, apes in Africa. The Andromeda we observe is not the Andromeda of today, but the Andromeda of the distant past. Stars have been born there since the light left. Stars have died. The structure has changed ever so slightly, but we cannot see those changes yet. We are looking at history, frozen in light, travelling across the void. The Virgo cluster, a collection of thousands of galaxies about 65 million light-years away, appears to us as it was 65 million years ago, around the time the dinosaurs went extinct on Earth. The galaxies we observe in Virgo are ancient images, preserved in the light that has been travelling toward us for longer than mammals have dominated the Earth. Every photon from those galaxies is a messenger from a time when the world was utterly different, when continents were in different positions, when life on Earth was unrecognizable compared to today. When astronomers point the Hubble Space Telescope or the James Webb Space Telescope at distant galaxies, they are deliberately aiming billions of years into the past. The Hubble Ultra Deep Field, one of the most famous astronomical images, shows galaxies as they appeared more than 10 billion years ago, when the universe was less than a quarter of its current age. Some of the galaxies in that image are so distant that we see them as they were only a few 100 million years after the Big Bang, when the universe was still in its infancy, when the first stars were just beginning to form. These are not just distant objects, they are windows into cosmic history, glimpses of a universe that no longer exists in that form. This time delay is not a limitation but a gift. It allows us to study the history of the universe directly, to see how galaxies have evolved over billions of years, to watch the cosmos change from a hot, dense state to the cool, structured web of galaxies we observe today. By comparing nearby galaxies to distant ones, astronomers can trace the story of star formation, the growth of supermassive black holes, the merging of galaxies, and the gradual assembly of the large-scale structure. The universe reveals its own history through light, and we are fortunate enough to be in a position to observe it. The farthest light we can see is the cosmic microwave background, the afterglow of the Big Bang. This radiation comes from a time when the universe was only 380,000 years old, when it had just cooled enough for atoms to form and light to travel freely for the first time. When we observe the cosmic microwave background, we are seeing the universe as it was in its infancy, a glowing plasma filling all of space, just beginning to transition into the transparent cosmos we know today. This light has been travelling for 13.8 billion years, stretched by the expansion of space from visible wavelengths into microwaves, but it is still here, still detectable, still carrying information about the earliest moments of existence. The consequence of light as a time machine is that the universe is not just a place but a timeline. Every direction you look shows you a different moment in history, layered around you in concentric shells of time. The nearest stars show you the recent past, decades or centuries ago. The nearest galaxies show you millions of years ago. Distant galaxies show you billions of years ago. And the cosmic microwave background shows you the beginning. You are surrounded by history, by light that has been travelling since before Earth existed, since before the Sun formed, since before the Milky Way took its current shape. This also means that if there are observers on a planet in a distant galaxy, looking back at the Milky Way with their own telescopes, they are seeing our galaxy as it was millions or billions of years ago, depending on their distance. They do not see us. They cannot. The light from Earth today has not had time to reach them. They see the Milky Way as it was long before humans existed, perhaps before Earth itself formed. And if we could somehow send them a signal today, it would take millions or billions of years to arrive, by which time their civilization might be long gone, replaced by something new, or vanished entirely. The fact that looking outward is looking backward also has implications for understanding the universe's structure. The galaxies we see are not where they appear to be. Because space has been expanding while the light travelled, the galaxies have moved farther away. A galaxy whose light has taken 10 billion years to reach us was much closer when the light left, but it is much farther away now, carried by the expansion of space. The observable universe is not a snapshot of the universe at one moment in time, but a patchwork of images from different eras, all stitched together by the different travel times of light. This creates a strange effect where the edge of the observable universe shows us the youngest galaxies, the earliest stars, the universe in its infancy. But those galaxies are not too young anymore. If we could see them as they are today, they would be old, mature, perhaps long since merged with others. We are seeing their youth, their beginnings, preserved in the light that has travelled across the universe to reach us. They are ghosts of the past, frozen in time by the finite speed of light. There is something deeply moving about this realization. Every time you look at the night sky, you are not just seeing space but time. You are witnessing history, observing the universe as it was, layer upon layer of the past stacked around you. The stars you see are echoes, their light travelling for years or centuries before arriving at your eyes. The galaxies are memories, their images carried across millions or billions of years. And the cosmic microwave background is the earliest memory of all, the first light, the glow of creation itself. This transforms how we think about observation. Astronomers are not just scientists but historians, archaeologists of the cosmos, piecing together the story of the universe from the light that arrives at their telescopes. Every image is a piece of the past, every spectrum a clue about conditions long ago. The universe writes its own history in light, and we are learning to read it, to trace the evolution of galaxies, the formation of stars, the birth of planets, all by studying photons that have been travelling since before we existed. As we sit with this consequence, we can appreciate the elegance of it. Light is not just illumination, but information. It is not just brightness, but history. Every photon is a time traveller, carrying news from the past, and by collecting those photons, by analysing their wavelengths and intensities, we reconstruct the story of the cosmos. We see not just where things are, but when they were. And in that seeing, we connect to a timeline that stretches from the present moment all the way back to the beginning, a continuous thread of light linking us to the birth of the universe itself. If light as a time machine is one profound consequence of cosmic scale, then the expansion of the universe is another, perhaps even more fundamental. The expansion changes everything: how we measure distances, how we understand the universe's history, and how we imagine its future. To truly compare the size of the Milky Way to the size of the universe, we must understand that the universe is not static. It is growing, stretching, carrying galaxies apart, and this expansion is woven into the very fabric of space itself. Tonight, let us explore the expansion story, the discovery that reshaped cosmology and revealed that the universe has a history, a beginning, and a trajectory that will continue far into the future. The story begins with Edwin Hubble, though the groundwork was laid earlier by others. In the 1920 seconds, astronomers had already established that galaxies existed beyond the Milky Way, and they were beginning to measure the distances to these galaxies using Cepheid, variables and other techniques. But Hubble added a crucial piece of information: the motion of galaxies. Using spectroscopy, he measured the light from distant galaxies and noticed that it was redshifted, meaning the wavelengths were stretched toward the red end of the spectrum. This redshift was consistent with the Doppler effect, the same phenomenon that makes a siren sound lower in pitch as it moves away from you. Hubble found a pattern. The farther away a galaxy was, the more its light was redshifted, and therefore the faster it appeared to be moving away. This relationship, now known as Hubble's law, suggested something astonishing. The universe was not static. Galaxies were receding from us in all directions, and the more distant they were, the faster they receded. At first, this seemed to suggest that we were at the centre of some cosmic explosion, with everything moving away from us. But further analysis revealed a deeper truth. Space itself was expanding. To understand this, imagine the universe as the surface of a balloon. Galaxies are like dots drawn on the balloon's surface. As you inflate the balloon, the surface stretches, and the dots move apart. Not because they are travelling across the surface, but because the surface itself is expanding. Every dot sees every other dot moving away, and the farther apart two dots are, the faster they appear to separate, because there is more stretching surface between them. This is what is happening in the universe. Space is expanding, carrying galaxies with it, and the expansion is uniform, the same everywhere, which is why every observer sees the same pattern of recession. This discovery had profound implications. If the universe is expanding now, it must have been smaller in the past. Trace the expansion backward in time, and you arrive at a moment when all the matter and energy in the universe was compressed into an incredibly hot, dense state. This was the origin of the Big Bang theory, the idea that the universe began in a singular event and has been expanding and cooling ever since. The Big Bang was not an explosion in space, but an expansion of space, a moment when time and distance began, when the universe went from a state of extreme density to the vast, structured cosmos we observe today. The expansion also explains why the observable universe is larger than you might expect. If the universe was static, and light had been travelling for 13.8 billion years, the most distant objects we could see would be 13.8 billion light-years away. But because space has been expanding while the light travelled, those objects are now much farther away, about 46.5 billion light-years in each direction, giving the observable universe a diameter of about 93 billion light-years. The expansion stretches not only space, but also the light travelling through it, which is why distant galaxies appear redshifted. In the 1,990 seconds, astronomers made another groundbreaking discovery. The expansion is accelerating. Two independent teams studying Type I supernovae, measuring their distances and redshifts, found that distant supernovae were farther away than expected if the universe's expansion was slowing down due to gravity. The only way to explain the observations was to propose that some force was counteracting gravity, pushing space to expand faster and faster. This force was dubbed dark energy, and it now appears to make up about 68% of the total energy content of the universe. Dark energy is one of the deepest mysteries in cosmology. We do not know what it is, only that it has a repulsive effect, causing space to expand at an accelerating rate. It may be a property of space itself, a cosmological constant, as Einstein once proposed. Or it may be a dynamic field, changing over time. Whatever it is, it dominates the universe's future. Because of dark energy, the expansion will continue forever, carrying galaxies farther and farther apart, eventually isolating them beyond the reach of light. The impact of the expansion on cosmic scale is profound. It means that the universe is not a fixed stage on which events unfold, but an active participant, growing, changing, shaping the fate of everything within it. Galaxies that are gravitationally bound, like the local group, will remain together, their mutual gravity overcoming the expansion. But galaxies that are farther apart will drift away, their distances increasing, until they disappear beyond the cosmic event horizon, the boundary beyond which they recede faster than light can travel. This also means that the observable universe will shrink over time, even as the physical universe grows. Galaxies currently visible will fade from view, their light stretched into invisibility by the expansion. In the distant future, hundreds of billions of years from now, observers in our galaxy, or the merged remnant of the Milky Way and Andromeda, will see only a handful of nearby galaxies. The cosmic microwave background will be stretched beyond detection. The evidence for the Big Bang, the expansion, the cosmic web, all will be gone, leaving a universe that appears static, small, and isolated. Future astronomers will not have access to the same clues we do, and they may never discover the true history and scale of the cosmos. The expansion story also changes how we think about the Milky Way's place in the universe. Our galaxy is not sitting still in space. It is moving, carried by the expansion along with everything else. But on small scales, where gravity dominates, the expansion is negligible. The Milky Way is not expanding. The solar system is not expanding. The distance between Earth and the Sun is not increasing. The expansion affects only the larger scales, where gravity is too weak to hold things together. This is why the Milky Way can maintain its structure even as the universe grows around it. Another impact of the expansion is on the concept of distance itself. In an expanding universe, distance is not a simple, fixed quantity. There is the distance light has travelled, the light travel distance. There is the distance an object was when the light left, the past distance. There is the distance the object is now, the present distance, also called the comoving distance. And there is the distance the object will be in the future. Each of these distances is different, and which one you use depends on what you are measuring. The expansion complicates comparisons, but it also enriches them, revealing the dynamic nature of the cosmos. The expansion story is also a story of time. The universe has a finite age, 13.8 billion years, which means it has a history. There was a beginning, a moment when time started, when space began expanding, when matter and energy first appeared. Before that, if before even makes sense, there was nothing that we can observe or measure. The expansion gives the universe a narrative arc, a past, present, and future. It transforms cosmology from the study of a static structure into the study of a dynamic process, an unfolding story that we are part of. The impact of the expansion extends to philosophy as well. If the universe had a beginning, does it have an end? If it is expanding forever, will it eventually become cold, dark, and empty, with all stars burned out, all black holes evaporated, all structure erased? This scenario, sometimes called the heat death of the universe, is the most likely fate given current evidence. It is a future so distant, trillions of years away, that it is almost beyond comprehension. But it is also a reminder that nothing lasts forever. Not stars, not galaxies, not even the universe as we know it. And yet, the expansion is also an act of creation. It creates space, stretches distances, and allows the universe to evolve. Without expansion, there would be no Big Bang, no cooling, no formation of atoms, stars, or galaxies. The expansion is not just a feature of the universe, but the process by which the universe became what it is. It is the mechanism of cosmic history, the force that allowed complexity to arise from simplicity, structure from uniformity, galaxies from gas. As we sit with the expansion story, we see that it is central to understanding cosmic scale. The universe is not just large, it is growing. The Milky Way is not just one galaxy among many. It is one galaxy in an expanding web, a structure being stretched, a participant in a process that has been unfolding for billions of years and will continue for billions more. The expansion changes everything, and to compare the galaxy to the universe without accounting for it would be incomplete. The story of the universe is the story of expansion, and we are living within that story, carried by it, shaped by it, witnesses to its ongoing unfolding. Behind every measurement of cosmic scale, behind every image of a distant galaxy, behind every calculation of the universe's expansion, there are people, dreamers who dedicated their lives to understanding something far larger than themselves. The story of how we came to know the size of the universe compared to our galaxy is not just a story of telescopes and equations, but a story of human curiosity, persistence, and wonder. Tonight, let us honor the observers, the individuals who looked upward and refused to accept that the stars were unknowable, who built instruments and developed techniques to measure the immeasurable, and who, in doing so, expanded humanity's sense of place in the cosmos. The story begins with the early astronomers, those who first questioned the nature of the stars and the structure of the heavens. Ancient Greek philosophers like Aristarchus proposed that the Earth orbited the Sun, and that the stars were distant suns, an idea so ahead of its time that it was largely ignored for centuries. It was not until the 16th and 17th centuries, with Copernicus, Galileo, and Kepler, that the heliocentric model gained acceptance, and even then, the stars remained distant mysteries, their true nature unknown. The breakthrough came with the development of spectroscopy in the 19th century, a technique that allowed astronomers to analyze the light from stars and galaxies, breaking it into its component colors and revealing information about composition, temperature, and motion. Joseph von Fraunhofer discovered dark lines in the solar spectrum, which were later identified as absorption lines from specific elements. This discovery opened a new window onto the universe, allowing astronomers to study not just where objects were, but what they were made of and how they were moving. One of the unsung heroes of early cosmic distance measurement was Henrietta Swan Leavitt, a woman working at the Harvard College Observatory in the early 1900s. At the time, women were not allowed to operate telescopes or conduct independent research. They were employed as computers, analyzing photographic plates and cataloguing stars. Leavitt was assigned to study variable stars in the Magellanic Clouds, and it was during this work that she discovered the period luminosity relationship in Cepheid variables. This discovery became the foundation for measuring distances to nearby galaxies, and yet Leavitt received little recognition during her lifetime. She died in 1921, never knowing that her work would become one of the cornerstones of modern cosmology. Edwin Hubble, by contrast, became famous for his discoveries. Working at the Mount Wilson Observatory in California, he used the new 100-inch Hooker telescope, the largest in the world at the time, to observe distant galaxies. It was Hubble who identified Cepheids in Andromeda, proving it was a separate galaxy. And it was Hubble who discovered the relationship between distance and redshift, revealing that the universe was expanding. Hubble's work transformed astronomy, and his name became synonymous with the expansion of the cosmos. The Hubble Space Telescope, launched in 1990, was named in his honor, and it has continued his legacy, imaging galaxies billions of light years away and measuring the universe's expansion rate with unprecedented precision. But Hubble did not work alone. He relied on the work of Vesto Slipher, who had measured the redshifts of galaxies before Hubble, and on the theoretical work of Georges Lemaître, a Belgian priest and physicist who proposed that the universe had a beginning, a moment of creation that he called the primeval atom, later known as the Big Bang. Lemaitre's ideas were initially met with skepticism, but they gained support as observational evidence accumulated. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson, two engineers at Bell Labs who stumbled upon it while trying to eliminate noise from a radio antenna, provided the strongest evidence yet that the universe had begun in a hot, dense state and had been cooling and expanding ever since. Element in astronomy is not just about individual brilliance, but about collaboration, about teams of people working together to solve problems that no one person could solve alone. The development of the cosmic distance ladder involved contributions from hundreds of astronomers over more than a century, each refining techniques, calibrating measurements, and extending the reach of observation. The construction of modern telescopes, from the ground-based giants like the Keck telescopes in Hawaii to space-based observatories like the James Webb Space Telescope, required the expertise of thousands of engineers, scientists, and technicians, all working toward the common goal of seeing farther and more clearly. There is also a human cost to this work. Astronomy requires patience, long hours, and often years of effort for results that may or may not come. Observing runs at remote telescopes involve sleepless nights, freezing temperatures, and the frustration of cloudy skies that block observations. Data analysis can take months or years, sifting through vast amounts of information to find the signals hidden in the noise. And even when discoveries are made, the path to publication and recognition is often long and competitive. Many astronomers spend their entire careers contributing to the collective knowledge without ever becoming famous. Their names known only to their colleagues, their work appreciated only by those who understand its significance. And yet, they continue. They continue because the questions are compelling, because the universe is beautiful, because the act of discovery, of understanding something new, is its own reward. There is a particular kind of joy that comes from seeing a distant galaxy for the first time, from measuring a redshift that reveals a piece of cosmic history, from calculating a distance that places an object in the larger map of the universe. This joy is not about fame or recognition. It is about connection, about reaching across the void with instruments and minds, and touching something far away, something ancient, something that expands the boundaries of what is known. The human element also includes the educators and communicators, those who take the complex findings of astronomy and translate them into language that the public can understand. Carl Sagan, with his poetic descriptions of the cosmos, made millions of people fall in love with the stars. Neil deGrasse Tyson, Brian Cox, and others have continued this tradition, bringing the wonders of the universe into homes and classrooms, inspiring new generations to look upward and ask questions. Without these communicators, the discoveries of astronomers would remain locked in technical papers. With them, the universe becomes a shared treasure, something everyone can appreciate and wonder about. There is also a deeply personal dimension to the human element. Every astronomer has a story about what drew them to the stars, a moment when they looked up and felt something shift inside. For some, it was seeing the Milky Way for the first time from a dark site, away from city lights. For others, it was reading a book, seeing an image, or hearing a teacher describe the scale of the universe. These moments are personal, but they are also universal. A reminder that the desire to understand the cosmos is part of what it means to be human. The observers, the astronomers, the engineers, the educators, all are part of the story of how we came to know the size of the universe. They are the ones who built the telescopes, developed the techniques, made the measurements, analyzed the data, and communicated the results. They are the ones who looked at the night sky and refused to accept ignorance, who saw mystery as an invitation rather than a barrier. And because of them, we can sit here tonight and talk about the Milky Way and the observable universe, comparing scales that would have been unimaginable to our ancestors. As we honor these observers, we can also recognize that we are part of the same tradition. Every time you look at the stars, every time you ask a question about the universe, every time you feel wonder at the scale of existence, you are participating in the same human endeavor that has driven astronomy for millennia. You do not need to be a professional scientist to be an observer. You only need curiosity, openness, and the willingness to look upward. The universe is there, waiting, and the act of observing, of wondering, of asking is itself meaningful. For all the progress astronomers have made in measuring the size of the universe and comparing it to our galaxy, there remain debates, uncertainties, and competing models. Science is not a monolithic structure where everyone agrees on every detail. It is a process of questioning, testing, refining, and sometimes disagreeing. The question of cosmic scale is no exception. Different techniques give slightly different results. Different assumptions lead to different conclusions. And different interpretations of the same data can lead to very different pictures of the universe. Tonight, let us explore some of these competing models and the debates that continue to shape our understanding of cosmic scale. One of the most significant debates in modern cosmology centers on the Hubble constant, the number that describes the rate at which the universe is expanding. Measuring the Hubble constant is essential for determining the size and age of the universe, and yet different methods give different values. When astronomers use the cosmic distance ladder, measuring distances to nearby galaxies with Cepheids and Type Ia supernovae, they get one value for the Hubble constant. When they analyze the cosmic microwave background using data from the Planck satellite, they get a slightly different value, lower by about 8 to 10%. This discrepancy, known as the Hubble tension, has persisted for years and shows no signs of being resolved easily. The Hubble tension is not just a technical problem. It may hint at new physics, something we do not yet understand about the universe's expansion or composition. Perhaps dark energy is not constant but changes over time. Perhaps there is an unknown component of the universe, something that affects expansion in ways we have not accounted for. Or perhaps one of the measurement techniques has a subtle error, a systematic bias that has not yet been identified. Astronomers are working hard to resolve the tension, refining measurements, cross-checking techniques, and searching for new methods. The debate is ongoing, and the outcome will shape our understanding of cosmic scale. Another area of debate involves the geometry of the universe. Is the universe flat, as current measurements suggest, or does it have some curvature? A flat universe would extend infinitely in all directions, or at least be so large that curvature is undetectable. A positively curved universe would wrap around on itself, like the surface of a sphere, making it finite in size but without edges. A negatively curved universe would have a saddle shape, also potentially infinite, but with different geometrical properties. Measurements of the cosmic microwave background indicate that the universe is very close to flat, so close that we cannot determine with certainty whether it is exactly flat or just nearly so. This uncertainty leaves open the question of whether the universe is finite or infinite, a fundamental question with profound implications. There are also competing models about the ultimate fate of the universe. The current evidence suggests that the expansion will continue accelerating forever, driven by dark energy, leading eventually to a cold, dark, isolated cosmos. But some models propose alternatives. If dark energy is not constant but weakens over time, the expansion might eventually slow, allowing gravity to pull the universe back together in a big crunch, the opposite of the Big Bang. Other models suggest that dark energy might strengthen over time, leading to a big rip, where the expansion becomes so rapid that it tears apart galaxies, stars, planets, and eventually even atoms. Each of these scenarios leads to a different picture of cosmic scale and its evolution. There is also debate about the nature of dark energy itself. Is it the cosmological constant, a fixed property of space, as Einstein proposed? Or is it a dynamic field, changing over time, as some theories suggest? Different models of dark energy predict different behaviors for the universe's expansion, and these differences can be tested with observations. But so far, the data are consistent with a cosmological constant, leaving the mystery unresolved. Until we understand what dark energy is, we cannot be fully confident in our models of the universe's size, age, or fate. Another area of competition involves the multiverse, the idea that our universe is just one among many, perhaps infinitely many. Some versions of inflationary cosmology, a theory about the universe's earliest moments, suggest that inflation creates countless bubble universes, each with its own properties, each expanding in its own region of space. In this view, the observable universe is just a tiny part of one bubble, and the full multiverse is unimaginably larger. Other physicists reject the multiverse as untestable and therefore unscientific, arguing that if we cannot observe other universes, we cannot make scientific claims about them. The debate is as much philosophical as scientific, touching on questions about what counts as evidence and what kinds of theories are acceptable. There are also competing interpretations of cosmic scale itself. Some physicists emphasize the observable universe, the part we can see, as the only meaningful definition of the universe's size. Others argue that the full universe, including regions beyond the observable horizon, is what matters. Even if we can never observe it, some see the universe as fundamentally finite, with a definite size and structure, while others see it as potentially infinite, extending without bound. These are not just technical distinctions, but different ways of thinking about existence, about what is real and what is knowable. The opposition and debate are not signs of failure, but of vitality. Science thrives on disagreement, on the clash of ideas, on the testing of hypotheses against observations. The competing models force astronomers to refine their measurements, to think more carefully about assumptions, to search for new evidence. The debates drive progress, ensuring that no conclusion is accepted without scrutiny, that every claim is tested and retested. And they remind us that our understanding is always provisional, always subject to revision in light of new data. One of the most interesting aspects of these debates is that they often hinge on very precise measurements. The difference between one value of the Hubble, constant, and another is only a few percent, and yet that small difference has profound implications. It is a testament to the precision of modern astronomy that such small discrepancies can be detected and debated. It is also a reminder of the challenges involved in measuring the universe. Every measurement comes with uncertainties, and those uncertainties accumulate, especially when you are climbing the cosmic distance ladder, building one measurement on top of another. As we sit with these competing models and debates, we can appreciate the complexity of the question we are exploring. Comparing the size of the universe to the size of the Milky Way is not a simple matter of measuring two distances and dividing. It involves understanding the expansion of space, the geometry of the universe, the nature of dark energy, and the limitations of our observational techniques. It involves choices about what to measure and how to interpret the results, and it involves accepting that some questions may not have definitive answers, at least not yet. The opposition also reminds us that science is a human endeavour, shaped by the perspectives and biases of the people who practice it. Different astronomers may emphasize different methods, trust different data sets, or favour different theoretical frameworks. These differences are not weaknesses but strengths, ensuring that the community as a whole explores a wide range of possibilities and that no single perspective dominates unchallenged. The debate is part of the process, and through it, our understanding becomes more robust, more nuanced, more accurate. There comes a moment, for many people, when the scale of the universe truly sinks in, not just as an intellectual fact, not just as a set of numbers memorized from a book, but as a felt reality. This awakening can happen in many ways. It might come while standing under a dark sky, seeing the Milky Way stretched across the heavens. It might come while looking at an image from the Hubble Deep Field, thousands of galaxies in a patch of sky smaller than a grain of sand. Or it might come while reading about the observable universe, 93 billion light-years across, containing trillions of galaxies. However it happens, the awakening is a shift from abstract knowledge to embodied awareness, and it often begins with a profound sense of smallness. You are small. This is not a value judgment or a criticism. It is simply a fact. You are a human being, about 2 meters tall, living on a planet about 12,700 kilometers across. That planet orbits a star, one of hundreds of billions in a galaxy, about 100,000 light-years wide. That galaxy is one of trillions in an observable universe, about 93 billion light-years across. At each step, the scale increases by factors of millions or billions, until your size, your life, your concerns shrink to almost nothing against the cosmic backdrop. You are a speck on a speck on a speck, so small that the universe would not notice if you disappeared, so brief that your entire existence is less than a blink in cosmic time. This smallness can feel crushing at first. It can make your worries seem trivial, your achievements meaningless, your life insignificant. If the universe is so vast, what does it matter what you do? If there are trillions of galaxies, billions of stars in each, why should your individual existence carry any weight? This is the dark side of the awakening, the moment when scale threatens to erase meaning, when the vastness feels not like liberation but like annihilation. But if you sit with the smallness long enough, something else begins to emerge. Smallness does not have to mean insignificance. You are small. Yes, but you are also aware. You are conscious. You can think, feel, question, wonder. And that awareness, that consciousness, is itself extraordinary. As far as we know, most of the universe is not aware of itself. Galaxies do not reflect on their size. Stars do not contemplate their existence. Planets do not ask questions. But you do. In you, the universe has become conscious, capable of looking back at itself, of measuring its own scale, of asking what it all means. This realization shifts the awakening from despair to wonder. You are small, but you are also a part of the universe, not separate from it. The atoms in your body were forged in stars billions of years ago. The oxygen you breathe was created by fusion in stellar cores. The carbon in your cells was scattered by supernovae. You are made of the same matter that makes up galaxies, stars, and planets. You are not an outsider looking at the universe. You are the universe, temporarily arranged in human form, aware enough to notice itself. The awakening also brings a shift in perspective on time. Your life is brief, perhaps 80 or 90 years if you are fortunate. Against the 13.8 billion years of cosmic history, your lifespan is negligible, a flash, barely long enough to register. And yet, your brief existence is when you are alive, when you can experience, when you can know. The universe may be ancient, but you are here now, in this moment, and that presence is not diminished by the vastness of time. If anything, the brevity makes it more precious, more urgent, more worthy of attention. The awakening can also change how you relate to other people. When you realize that every human being shares the same cosmic address, the same small planet, the same brief lifespan, the divisions between us can seem less important. We are all, together, inhabitants of a tiny world in a vast universe. The borders we draw, the conflicts we fight, the differences we emphasize, all shrink against the backdrop of cosmic scale. This does not make those things disappear, but it can soften them, can provide perspective, can remind us that we are all in this together, fellow travelers on a small island in an immense ocean. Another aspect of the awakening involves humility. Before you understand cosmic scale, it is easy to imagine that you, or humanity, or Earth, might be central, important, special. After the awakening, you know that we are not central. We are not at the middle of the galaxy or the universe. We are not unique in structure or composition. We occupy no privileged position. The universe does not revolve around us. It does not care about us in any intentional sense. This humility can be uncomfortable, but it is also grounding. It frees us from the burden of needing to be special and allows us to appreciate what we are. Participants, not rulers. Witnesses, not the center. The awakening also opens the door to gratitude. To exist at all, in a universe this vast, is remarkable. The odds of your existence, when you trace back through the history of the cosmos, are vanishingly small. If the Big Bang had unfolded slightly differently, stars might not have formed. If stars had not fused heavy elements, planets like Earth would not exist. If Earth had not formed in the right orbit, with the right conditions, life might never have arisen. And if life had not evolved over billions of years, leading eventually to humans, you would not be here. Your existence depends on a chain of events so long and so precise that it seems almost miraculous. To realize this is to feel gratitude, not for any particular agent or design, but for the simple fact of being here, now, able to experience and reflect. The awakening also changes how you think about meaning. Before, you might have thought that meaning needed to be large, cosmic, eternal. After, you realize that meaning is not about size or duration, but about awareness and connection. A sunset is meaningful not because it lasts forever, but because you notice it, because it moves you. A conversation is meaningful not because it changes the universe, but because it connects you to another person. Meaning arises in moments, in experiences, in relationships, and it does not need to be vast to be real. This awakening, this realization of smallness and its transformation into belonging, is one of the deepest gifts that understanding cosmic scale can offer. It challenges our assumptions, undermines our sense of importance, and confronts us with the limits of our lives. But it also opens us to wonder, to humility, to gratitude, and to a sense of connection that transcends the boundaries of self. To realize our smallness is not to be diminished, but to be placed in context, to see ourselves as part of something larger, to understand that we belong to the universe, not as its masters, but as its children. And so we return to where we began, standing beneath the night sky, looking upward at the stars. But now, after this journey through cosmic scale, after exploring the size of the Milky Way and the vastness of the universe, after climbing the cosmic distance ladder and pondering what it all means, the stars feel different. They are no longer just points of light, but suns, some with planets, some with histories stretching back billions of years. The faint band of the Milky Way is no longer just a glow, but a structure, a galaxy seen from within, 100,000 light-years across, containing hundreds of billions of stars. And the darkness between the stars is no longer empty, but filled with the knowledge of distant galaxies, trillions of them, scattered across 93 billion light-years of space, each an island of light in the cosmic ocean. Tonight, as we close this exploration, let us rest beneath the stars with all of this knowledge gently held in mind, not as a burden or a weight, not as something that overwhelms or diminishes, but as a context, a framework, a way of seeing that enriches rather than reduces. The universe is vast, yes, but that vastness is what makes it wondrous. The Milky Way is small compared to the universe, yes, but it is also our home, the structure that contains us, the galaxy we belong to. And we are smaller still, yes, but we are also aware, conscious, capable of understanding the very scale that humbles us. As you lie here, whether in bed or in a chair or simply sitting quietly, let your breathing slow. Let your body settle into the surface beneath you. Notice the weight of your limbs, the rise and fall of your chest, the quiet rhythm of your heartbeat. You are here, in this moment, in this body, on this planet, in this galaxy, in this universe. Each level of scale is real. Each is present. Each is part of your existence. You do not need to choose between them. You can be both small and significant, both local and cosmic, both finite and connected to the infinite. The stars above you, whether you can see them through a window or simply imagine them beyond the ceiling, are the same stars that have shone for billions of years. They are the same stars that ancient humans looked at and wondered about, that sailors navigated by, that poets wrote about, that lovers gazed at together. They are the same stars that will continue to shine long after we are gone, indifferent to our presence but beautiful nonetheless. To rest beneath the stars is to participate in a tradition as old as awareness itself. The simple act of looking up and feeling connected to something larger. Let the knowledge of cosmic scale settle gently into your awareness. The Milky Way is 100,000 light-years across. The observable universe is 93 billion light-years across. The universe is about 1,000,000 times larger than our galaxy in diameter, billions of times larger in volume. These numbers are enormous, but they do not need to be held tightly. They can rest in the background, a quiet reminder of the vastness, while you attend to the smallness of this moment, the intimacy of your breath, the warmth of your body, the softness of rest. There is no contradiction in this. You can know that the universe is immense and still find meaning in the small. You can understand that galaxies number in the trillions and still care deeply about the people in your life. You can grasp that time stretches back 13.8 billion years and still value the fleeting moments of a single day. Scale does not diminish meaning. It contextualizes it, placing your life within a larger story. But that story includes you, honors you, holds space for your experience. As you drift towards sleep, if that is where this moment is taking you, let the stars be your companions. They are distant, yes, but their light reaches you, bridging the void, connecting you to places and times far beyond your own. You are not alone in the darkness. You are surrounded by light, by structure, by a universe that, while indifferent, is also beautiful, ordered, filled with patterns and processes that have unfolded over cosmic time to bring you to this moment. Let go of the need to grasp everything, to understand fully, to hold the entirety of cosmic scale in your mind all at once. It is enough to know that the universe is vast, that your galaxy is small within it, and that you are small within your galaxy. It is enough to feel the awe, the humility, the wonder. It is enough to rest, to breathe, to be present. The universe will continue its work. Galaxies will drift, stars will shine, space will expand, and you can simply be here, now, held by the same gravity that shapes galaxies, breathing the same atoms that were forged in stars, participating in the same story that began with the Big Bang. If you found comfort in this journey, if the exploration of cosmic scale brought you a sense of peace or perspective, you might return to this space again, whenever you need to remember the vastness, whenever you need to feel small in a way that is liberating rather than crushing. You might share this journey with someone else who is seeking calm, who is looking for a gentle way to engage with the immensity of existence. Or you might simply let it rest here, in your memory, a quiet understanding that you can return to when the world feels too close, too immediate, too overwhelming. The Milky Way is your home, a galaxy among trillions, vast beyond everyday comprehension, yet small against the universe. And you are at home within it, a brief flicker of awareness in an ancient cosmos, small yet significant, fleeting yet meaningful. The comparison between galaxy and universe is not just about size. It is about perspective, about seeing where you fit, about understanding that you are part of something unimaginably large, and that your participation, however small, however brief, is real and valuable. As the stars continue their slow wheel across the night, as the Earth turns beneath you, as the Milky Way orbits its center, as the universe expands outward in all directions, you can rest. You can let go of the questions, the comparisons, the measurements. You can simply be here, beneath the infinite, held by the finite, breathing in this moment, grateful for the chance to wonder, to know, to feel. The universe is vast, and you are small, and both of these truths are beautiful. The night sky will be there tomorrow, and the stars will shine again, and the questions about scale and size and meaning will remain available for whenever you wish to explore them. But for now, rest. Let the vastness hold you gently. Let the smallness feel like home. Let the comparison between the Milky Way and the universe remind you that you belong to both, that you are local and cosmic, finite and connected to the infinite, a temporary arrangement of atoms that has become, for this brief moment, aware of the whole. Good night. Rest well. The universe is vast, and you are part of it. That is enough. That is more than enough. That is everything.